Yes. Yeah. So I don't know. I am here.
Yeah. Okay, now you're ready, I guess.
Yes, I am. I wait for somebody asking me to do, I don't know what.
Yeah, I don't know who the chair is, but I suppose.
Okay.
Can you see the audience, Giuseppe?
Yes, I'm ready. Hi. Hi, George.
All right, more or less. I'm the speaker, the guy with the blue mask.
Yes. Hi, ciao.
Not the speaker, sorry, the chair.
Yeah. Yeah. Shall I share the screen?
So your talk will be 25 minutes plus 5 for questions. I will warn you because I think you won't very easily see the...
Yes, this is very important. Okay, thank you. Yes, I put here. I do not put full screen because I think everybody can read this. First of all, do you see it?
Yes,
Yes.
your slides are clear.
Is it readable?
Yes.
From here, yes.
Okay.
Oh, me, yes.
Yeah. So just tell me when I can start.
All right, so we will start the first afternoon session. It's a pleasure to have virtually with us Giuseppe Vitiello. I sat down so he could see me. He will tell us about neutrino mixing, entanglement, and the gauge paradigm in quantum field theory. Please, Giuseppe.
Yes, thank you. Well, first of all, thanks to all the organizers for such a conference, which we needed, because a conference on standard model and these things, everybody's talking in these days. I mean, all the talkers or invited and speakers. Is something which makes alive the community in any way, even if just on at the level of electromagnetic images, namely visual participation like now. So since time is short, the title already tells you something, but let me go in the middle of the problem, namely in this in this gauge paradigm of neutrino mixing, which is something which happened to us, I mean, especially in Salerno with Massimo Blasone, Antonio Capolupo, and all people here in the group, to work on just a few years ago, but is still something on which we are thinking and doing some more. Then I will say a few words on entanglement too, on the entanglement of the vacuum. By the way, Massimo Blasone will have his talk on Saturday, I think, according to the schedule. In any case, well, let me start from the point which has been a central object of our investigation in these years, which is the fact that it is possible to define a vacuum state for the flavor neutrinos, which is not so easy to understand in some sense, unless you go to a quantum field theory framework, not just quantum mechanics, because in quantum field theory you have infinitely many unitarily non-equivalent, inequivalent representations of the canonical, in this case, anti-commutation relations. So there is room for flavor quantum number in a new representation. And this is a point, by the way, which is under investigation just in this time in our discussions in Salerno. So you define a flavor state. I will not tell you how do you do. I will show you how it is made as a condensate of neutrino antineutrinos pairs. Actually, it is an SU2 coherent, generalized coherent state, and it is an entangled state of such couples of neutrino and antineutrinos. And in this quantum field theory treatment of mixing, you find that such a vacuum is dependent on time. This, at first sight, is a problem because the Lorentz invariance is broken. But this means that at each time you have a new representation. So at each time you find yourself on the Poincare group, which you might define in a flat space tangent to such curved background, which in this case is related with time flowing. These aspects have also attracted the attention of several people in the sense to make a relation between neutrino mixing in association with quantum gravity effects, as indeed as quantum gravity induced decoherence into neutrino oscillations, which has to do with many of the measurements. Of course, you have Lorentz violations and the CPT symmetries. We have been listening this morning, beautiful talks, but not only this morning, about these CPT symmetries. So all this matter, neutrino mix is very interesting as a problem, neutrino mixing, because it includes so many facets, so many aspects of quantum field theory, of particle physics, that is really a richness in some sense to be investigated. So I would like to clarify about this gauge structure by showing that the non-abelian structure, gauge structures, appears naturally in connections with flavor mixing. This looks strange at first sight because you think just of particle, but the gauge paradigm, the possibility to have a gauge structure within quantum field theory, is a characteristic, a founding characteristics of quantum field theory since the beginning. Just think of electrodynamics, of course. And this might be one possible way to look at such a violation of the Lorentz invariance. So let's go in the middle of the problem and take the usual standard Lagrangian written in terms of flavor fields. I will specify how you write these flavor fields. Here M is the non-diagonal matrix made by such quantities, which are the usual one you find already in the Pontecorvo paper, namely at the quantum mechanics approximation level. These terms, M in mu, is the one which controls actually the mixing. So where we find such a term, we will talk of mixing terms. In fact, if you derive in the standard way the field equations from such a Lagrangian, you find what is written here. You see, these are two equations, one for the electron neutrino, the other one for the muon one, where the object, the neutrino, let's say the electron neutrino in the first equation, it does not appear by itself alone, but there is a mixing term. There is a new mu coming in the same equation. So if you just look at this equation in a very easy way, I will show you, you might think of this term as a gauge field underlying and controlling the time evolution, namely the equation, the space-time evolution, namely the equation for the electronic neutrinos. In the second equation, you reverse the role. So you find that the monic neutrino is, here I'm talking only of the 2 flowers, but you can talk of 3 flowers, as we have 3 of them. What I'm saying as a structure which is completely general. Here I use 2 just for simplicity. The notation is the usual one. Alpha and beta are Dirac matrices, and etc. So you can rewrite these equations in this way by introducing a covariant derivative, which here is called the D0 at this level, and such a matrix which is now a diagonal matrix in the flower masses. This fact of the flower masses is a crucial point in this discussion, because normally flowered neutrinos, they are not eigenstate of an Hamiltonian for any time, but for fixed time, you can define, I will show you that, you will find an Hamiltonian which you can associate to an object of mass ME or M mu. So D0 is defined in this way. You see, there is the usual time derivative you have in the equation, but then we use that mixing term that was in the equation, we write it in this way, where sigma 1 is the Pauli sigma 1 matrix, and M in mu written in terms of difference of flowered neutrino masses, which you can write, of course, also in terms of massive neutrino masses, but is convenient here because everything is in the flower sector, let's say in the flower field sector. You might write in this way. Now, at this point, you do realize, I mean, what is written here and what is written here, this is a covariant derivative with respect to a covariant, to a gauge field A mu, which is defined as you take from here, 1/2 A mu A is internal degrees of freedom, sigma A. You can write with n mu multiplied this business you have within here. And n mu is, of course, 1, 0, 0, 0, because you have only the time part of it. So you see, this is the root of the breakdown of Poincare invariance. Now, since you have only the temporal component in space-time and only the first component in SU2 space, you get all the specifications in the flower space, in the space of the flower space of which I was announcing at the beginning. So this covariant derivative with such an mu, now you can write for any index the mu, of course, because in the other set, the space-time, the space terms are 0, but you can write in this way, and you can, and then you can write in terms of this d mu, the Lagrangian, and this is the previous MD, which I did show you. Now, when you have a maximal coupling, namely theta equal pi fourth, the coupling constant goes to infinity, while the mu goes to 0. And this is what is well known in the machinery of a neutrino mixing, but here it acquires the flower of a coupling with such a gauge field. You might define it as usual you do, an F mu nu A, M mu nu A is the internal index in the usual way, and this is always 0. But it happens that although this vanishes identically, you do have an effect of a gauge field, a physical effect. And this reminds us of the Aharonov-Bohm effect, where you do have 0 gauge in a region which, however, gives you some effect in the observation. Now you can work out as in a standard way the energy momentum tensor, which is written here. And you see the structure is what you do expect. And you might compare with the canonical T rho sigma, and now this eta is the Minkowski matrix. And this one is this. So you see, the only terms which is missing in this T tilde rho sigma is the mixing one, namely this one, which you do find if you derive it in a canonical way. This you find here because you have it is hidden inside these two parts with the covariant derivative, namely the difference. What I'm saying is indeed these terms. So this tensor T mu nu tilde, this one is not conserved on shell, because you have that gamma mu with d0 does not commute, and then this is different from 0. So you see, the 0 component of it is not conserved. So you cannot write it for any I equal to 0, for any including also time index. The d0 is not 0. And if you take out the mixing term in the covariant derivative, it would have been conserved, because it comes exactly from such a d0 at non-commutativity. With such object, T mu nu tilde, you might construct as usual 4 momentum objects P mu, which is the integration over space of T tilde 0 mu. And so you have the 3 momentum, and you have the Hamiltonian operator, whose explicit expression is given here. Now, these objects, they are interesting because they split, there is no mixing part. I mean, you have a contribution from the electronic part, neutrino electronic, and from the muonic component. And the same for such an Hamiltonian. But please notice, this Hamiltonian is not the one which is generator of time translation. That one is the full Hamiltonian, where such a splitting between electronic and muonic part is not completely possible, because you have one more term. Of course, you can construct all the Poincaré structure, namely also the other Lorentz generator, and all of it is time dependent. You see, they depend on x0, which you find everywhere in these definitions. So this is what I was saying at the beginning. You can construct a Poincaré structure at each time. And as time evolves, you go from one Poincaré structure to another one. Okay, thank you. I saw the 10 minutes. Yes, thank you. I will try to squeeze all of it. So now, by using the machinery which you can imagine, on which I squeeze, I do not spend much time on details. You write your field equations for your spinor objects, the wave which came in the fields, and you define an omega with such flavor masses, and you can do everything in the standard way. You might even realize that you have independence from such a specific tilde definition in the objects I was writing before, because you have the possibility to move around between your Poincaré structures at each time x0 through such Bogolyubov transformation generators, which J, which is given here in its explicit way. And you define a state, a vacuum state for such an object, which is this one, namely applying J minus 1 to the vacuum. Sorry, this should be this is the vacuum non-tilde. So the original, you fix one reference vacuum, and then you can move around this vacuum. So you have a non-conserved flavor charge, you might define also, and I will give you after, but before that, sorry, let me show the writing of the annihilation and the creation operators. Here I give you only the annihilation operators, flavor annihilation operators in terms of the massive operators. neutrino, always I'm thinking, massive ones. So you see, you have a rotation part, cosine theta, sine theta, but you have also these pieces. So this is like a box in another box. This part comes in the red one, the red part comes from the Bogoliubov transformation. And this is strictly connected, connected with the rotation, with what appears as a rotation. But if you use field theory, you do not have just rotation. In fact, the mixing transformation is a rotation transformation plus a Bogoliubov transformation. This plus is an algebraic plus. I mean, it is something quite strong to I mean, not easy to, not transparent. I mean, you can write as we do, but is hidden, let's say, in the structure. So you construct this vacuum for mu out of such transformations in this way, and this is the vacuum for the massive neutrinos. There are details, formal details. The G, such a generator of the mixing of a field is written in this way in terms of the 1-2 objects, and the U and V are two quantities which came in the problem, are very important. The modulus square, the sum of the modulus square of the two is 1, and their form is indeed of this kind. Now, I told you that you can write a flavor charge. Indeed, you can do. And here are written. I have not much time to comment, but you see, you have this part, which comes from the mixing of 1-2. So you cannot split. You cannot write this flavored charge, in this case E, QE, in terms just of Q1 and Q2. You have also terms which is there because you cannot separate anymore. This fact that you cannot separate anymore Ni1 and Ni2 is a crucial point which also experimentally should be taken in care. Is wrong if you just consider that at the vertex you generate a cosine square at some power of Ni1, and then you forget about the Ni2. There is no possibility. This is wrong. You will get, I mean, it could be an approximation, but it's a very, very rough approximation on which you cannot rely in any case. So you should not even think of a separate charge in things in terms of 1 and 2. You have always another piece there. So you can define all the space, which on the basis of such tilde objects I've written for you before, and you have a common set of eigenstates, commutation relation, you have all the algebra, and you have the state which is eigenstate of such charge. Sigma is E mu, the index here. So you have you have the whole Hilbert space structure. Now, here is written what I've been telling you, and you might, this is an interesting point, that you might think of such an H tilde, yes, thank you, as a free energy. This is very interesting because now you get a thermal picture. But such a thermal picture is actually not something surprising, because we do know that the gauge field in any theory, even the most familiar one in electrodynamics, has a behavior as a thermal reservoir, because it accounts for the reshuffling of the charge, which is a local gauge transformation, and it keeps the Lagrangian invariant even if you change the relative phase of the charge in that case. Here, again, you have the same kind of, and if you take the H, which is responsible of the time translation, I mean, the difference between one and such an F, which is H tilde, you find that the quantity you obtain is entropy, is proportional to T, temperature, times entropy. And the entropy looks like what looks like the mixing of electron and muon neutrino with such one alpha dm in front. And the G in all this business here, namely the tangent of 2 theta, looks like the coupling constant. So G is, you see, it depends on the mixing angle. If mixing is 0, G is 0. There is, you lose such a gauge structure and you get free Ni1 and Ni2, which is not the case. So you can think of mixed neutrinos, namely flowered neutrinos, as open systems. Systems continuously and once forever interacting with a gauge structure, which is the flowered, which describe, I mean, gives you the structure of the gauge vacuum, which is this one. This is the beautiful object, the flowered vacuum. You see, is made by couples of neutrinos and antineutrinos of different 1 and 2, you see, of a different mass index. And you find also parts like this one, where you have both of them, and you have, so you have at the end of the story 4 kind of particle-antiparticle pairs with 0 momentum and the spin, because this is a vacuum. This is a true flower vacuum, the one where we do live. Every experiment where you can measure a flower, you have a particle carrying a flower charge, then the vacuum you live in is such an object which is written here. There is no way out. This is quantum field theory. This I did show already. Here, the point to show it again is that you can measure the linear correlation coefficient J between numbers of A and B neutrinos, according to different what you choose that you want to be A and B, and this gives you a measure of the particle entanglement. You define all the objects here, and you find that entanglement between I and J stay for 1 and 2. So alpha annihilation operator of neutrinos I, let's say 1, and 2 J, because I is different from J, but also they can be the same. That is 0. They are not. Why? Because they do not come in the Bogoliubov part. You see, A1 and A2, they came, A2 comes still in this rotation part. So there is no entanglement between these two guys. In fact, J is 0. On the contrary, if you take alpha I and beta J, then you find that is a quantity more higher than 0.5 by taking as a square tangent what you find in the current table of mixing values and parameters, whatever. I mean, sin square of theta is whatever. So they tell me that is 0 time. So I skip any other detail on this mixing, which is already published since a long time. But just tell you, I would like to tell you that all of it might have, let's say, an optical a description in terms of quantum optics. Namely, can be described as in terms of a vacuum behaving as a refractive medium. And you can show that step by step. And I leave you to the curiosity, I mean, of each of you, how to go through this path. But this is a published result. So yes, I cannot go further also because I finished my slides. So thank you very much.
All right, let's thank the speaker. Thank you for rushing in the end. So we have time for questions. I see one over there in the back, please, Claudia. The microphone is going there. Over there in the pink shirt. Thank you.
Thank you for the nice talk. I have a question concerning the gravitational case. I mean, so you break essentially in this formalism, you break Lorentz symmetry, right? So So what happens if you have consider a coupling of the stress energy tensor to gravity? I mean, is there, for instance, something you get? I mean, you know that in gravity, I mean, you get the Urru effect or other effects depending on the frame of reference. How does this framework changes in the case of gravity? You are saying something about it, right?
The structure I have presented remains, and you have a beautiful aspects, indeed, with Urru effect, for example, and you have in the literature papers by Blasone and other people, where such an object is studied, and even you might relate that with Tsallis entropy. This is very how to say, fascinating from an algebraic point of view, because all things, they converge together. Actually, what is the problem? The problem, what is the discovery of the mixing of a particle, and especially with neutrinos, which are so pervasive, they are everywhere. When you mix two objects with different masses, which is forbidden if you have only quantum mechanics available to you, namely you have just one representation, then you cannot do it. You cannot, I mean, there are theorems. But if you have a quantum field theory, that mixing, you generates new quantum numbers. And the mixed field, they represent the confinement, let me use such a word, the confinement of the mixed neutrinos in our case, present case. So it is like Ni1 and Ni2 are confined, and they show up in terms of a new quantum number, which is the flower. So this is a way to generate quantum numbers, given some you start with. Now this happens, this is the teaching of this talk, this happens only if you have a curved background. And the curved background sends you, I mean, of course, to a vision of quantum gravity or things like that. I cannot give you a complete answer about such a problem because, I mean, everybody works also on this, and we do not have still a clear view. But here we did find why you have such a breakdown. It's not me or us that are breaking Poincare invariance, or Lorentz if you want. It is nature. Since you do have a new flower, a new quantum number, which is flower, because you have electrons, muons, and tau, nature needs a curvature. In this case, the curvature is this timeline, and at each point of such a curved timeline, you find a tangent Poincare structure, and as you move, you go from one Poincare flat time to another one, because it's a curvature. It's like with horizon, when you look, that is in space, of course, when you look at a boat which disappears behind the horizon because you have a curvature, and the optics goes line, I mean, the ray of light goes in a straight line on a plane tangent to the place where you observe.
Okay, thank you. We have two more questions. We'll address first the one from Zoom. Nick Mavromatos, you can unmute and ask your question, please.
Yes, a very nice talk, Giuseppe. I liked it. One question is, you have, of course, the same effects in the quark sector. Am I right? I mean, you.
Yes. You see, I mean, I know you are a bad guy. You are saying that this is the reason why I use the word confinement.
Precisely. That was my question. So, do you think there could be visible effects in the quark sector from the experimental point of view? I mean, neutrinos, of course, they are elementary particles, so it must be easier to see this. But do you think these oscillations between, you know, of course, you have electromagnetic effects there, so you don't have easily visible oscillation. But do you envisage some observable effects?
You see, I do not know, but what I mean, this is just guessing or fantasy, let's say. There, perhaps such a curvature is very strong. is such strong that you just have hadrons.
Right.
And you have to postulate such quarks, because nobody saw quarks unless you study jet in a very short fraction of time. But the curvature has to be so strong that you are no more able to look inside.
I see.
And
that's the confinement, you say.
And that is confinement. And that is beautiful, because it's not matter of energy, as we learned. I mean, I learned when I was a young student. It's not matter of energy. It's something more.
Right.
It's indeed a gauge structure. The quarks are always definitively interacting among themselves, and all of it constructs a gauge structure, and they are no more free,
right,
to separate. But I mean, I do not know how to show you a number on this point.
Full answer. Thank you very much. Very beautiful work. Thank you.
We have one final question from Alexei.
So I have very naive question. You see, flavor, we know, is very vague notion. It depends on energy. It depends on the process. It depends on many other things. So right way and consistent way is just to treat the problem in terms of mass states. And then there is the issue of coherence. That's it. So you have mass states, you have production of mass states, you have asymptotic states. There is no any inconsistencies in this. And then the question is coherence, if you want to have oscillations.
Absolutely. Coherence, I did not dare to use such a word, because all the quantum people living still today, just before 1928, Dirac equation, they live only of decoherence. I mean, but we know in particle physics. I mean, this SU2 flavor state. This is a coherent state.
Yeah, and I think
that does not cohere.
Let me finish and then you can check. So you see, till now, and I studied many questions, many kind of papers of the type that all kind of attempts to have a consistent theory of flavor and evolution of the flavor, they failed. We just use mass states, that's it. And there is not any kind of problem. Now I have the same question as Nick. You want to create something new, or so. Then the question is, what is a really observable effect which distinguishes this standard and naive question, naive picture, which I have described, from what you are doing?
Yeah, well, the fact that if you generate in a vertex a neutrino, that neutrino has a flavor number and is not made of Ni1, Ni2, and Ni3. You see, this is like to say to a small kid that to make a pie, you need sugar, flour, I don't know, eggs, something. Okay. Then to make a pie, you need that. But once the pie is made, it is not made by eggs, sugar, and flour. It's another identity. This is the point. Once the flavor number is generated, that is the pie where you cannot look inside.
You can produce, you can treat the problem just studying production of mass states. You have Lagrangian, which you can write in terms of mass states. Forget about the flavor.
For you, the tilde one, that is the one. And then, and then you have to do, you have to deal with an entropy problem, which I did show you. You can show more exactly what entropy is there. And this is the pie. This is the pie. It's something new, something which did not exist in terms of Ni1 and Ni2. If you want to do an exam of how the pie is made, and you send the pie to a lab where they make the analysis, then they find that it's made by eggs, but they destroyed the pie, either one. Or you eat the pie and you like it or not. Okay, that is another problem. or you destroy it.
We
Pi is not made by a
get the next speaker, but of course this session is recorded. The slides are here, and you can find each other emails to continue the discussion if you desire. So
Yeah.
we'll pass. Thank you again. Let's thank again Giuseppe.
Bye. Thank you.
And now we will pass swiftly to the talk by my colleague Jean Penel, who is going to tell us about something which was asked on my talk. He's going to talk about the kind of predictions you can make, in this case of mass hierarchies from residual modular symmetries. So as we finish setting up his talk.
Can you make it full screen, please?
Right, please, João.
Okay. Let me start the time. Hello, everyone. Thank you, Ivo, for this introduction, and thank you also for the organizers for the invitation and for setting up this wonderful workshop. So, as Ivo was saying, I will talk to you about modular symmetry, but pay no attention for now to the very technical title. I will present a work done this year with Sergei Petkov and Pavel Novichkov, but I will start with something more basic. So this is my outline. Why modular symmetry? As usual, motivation. How? So how do you use it if you want to build your own modular symmetric model? And finally, what is new? So what is this paper that I have in the title? Okay, so why modular symmetry is we can start with the usual slide, which you have seen 20,000 times in your life. So there we have hierarchies of the fermions, which you cannot explain naturally in the standard model. They also mix in some peculiar ways. And just a couple of slides on neutrinos. So we know some things about neutrino mixing from oscillations. We just don't know how the small and large mass square differences are ordered, or what is the absolute mass scale of neutrinos. Otherwise, let me flash the data, but pictorically what we have is a preference for NO over IO, and 2 large mixing angles and 1 small. The value of delta we're trying to constrain. So the question is there some organizing principle which can help us explain all this? And at this point, if you really like symmetry, you go on this direction, and I actually like symmetry quite a lot. So the idea is to try to use something it would be great if we could do something like gauge symmetries, right? So which unify vertically the fermions. But we need to go horizontally, and this is what flavor symmetries can do for us. Okay, now the usual approach to flavor and flavor symmetries, typically it relies on something like a discrete group, non-abelian flavor groups. And they can constrain the mixing and the Dirac phases and so on. But sometimes these kinds of models bring about problems. As was discussed, they can have a lot of flavons, which have to be aligned in some particular directions, and then your potentials go crazy and fill 100 pages. You need some shaping symmetries to make it look nicer. You have maybe no control even in supersymmetric theories of a tower of non-renormalizable operators. So the attempt here, the idea is that modular symmetry could be an improvement over this feature. So this is the idea put forward by Ferulio. There is instead of a flavor group GF, there is a modular group, which is capital gamma. It's not super just because it is an improvement, but it also requires supersymmetry for predictivity. Okay, and it's a nice setup. It can constrain the masses and the mixing. And if in its minimal implementation, this is maybe what is great motivation. We don't need the flavons. So we can use, if you want, one flavon, which is just a complex number, which is called the modulus tau. So this product is certified flavon-free, if you wish. And this is it. This is the motivation. So of course there is a dream that maybe we can naturally explain everything with just this paradigm with very little parameters and so on. We're not there yet. We are trying to go in this direction. Okay, so now you know the why. what about the how? So how do we build a model of a modular flavor model? And the first thing that I want to tell you about this tau, this complex number. From the top down, maybe it comes from some, may come from some compactification of a torus. Okay. From the bottom up, actually, we work with this and we don't care so much. It's a dimensionless Fourier, but it may describe a torus compactification. What this means is that if you have two different values of tau, tau and tau prime, you are describing different shapes of tori. Well, it turns out that there is a redundancy here, because if it happens that tau prime is related to tau in this way, with A, B, C, D are integers, with this relation, then actually you're just describing the same donuts, okay? So there is a kind of symmetry, which is a redundancy, which is basically all the set of transformations that take tau to this A tau plus D over C tau plus D. You can put A, B, C, D in a matrix. So all these matrices form a group, which is the modular group. Okay. And this is indeed at the heart of the approach. There is a field which transforms like this under the group. And as Ivo was saying this morning, we don't want to give you all the elements of the group. They are infinite, by the way. So we just present it in terms of generators. Maybe you also don't care about these equations, so let me give you a mnemonic. The modular group is generated by three generators, S, T, and R. S is the one which takes tau to minus 1 over tau. So if you want it's an inversion. Then T takes it to tau plus 1, so it's a translation. And R actually does nothing to tau, but it may act on the field, so we keep it for now. Redundant, in a sense. Okay. Now, the final point I want to make is that as soon as you choose your donuts, your shape of torus, you are fixing the value of tau, and you break the modular group. And that's it. I mean, no more flavons if you wish. Maybe you can get away with just using tau. So you have tau. What about the fields? Because we want to, in the end, we want to arrive at the standard model or something like that. So the fields will also transform under the modular group. And we want to know how, so we can build superpotential and so on. So the fields will transform in a way that generalizes the usual transformation of flavor symmetry. There is this new part which depends on the coefficients, on the entries of the gamma matrix. And so aside from you have to specify what is the weight of the field. This is the new part. The rest is just something which is similar to the discrete symmetry approach, where you mix the field with a rotation matrix flow. Okay. Now, as I said, the group is infinite. So the insight here is that this rho is acting trivially in most of the modular transformations. Okay, so it's you have an infinite group. There is an infinite subgroup, which is normal within it, as Ivo said, and you can conjugate it out. So divide one by the other, and you turn out to get a finite finite group. So this rho turns out to be a representation of a finite group. Okay. Good. So it's if the weight turns out to be 0, then we are in the familiar picture of flavor symmetry. Now, what are these groups? Do we know them? And the answer is yes. These groups, which are the quotients, and effectively are the ones whose representations we care about for rho. They are the usual groups: S3, A4, S4, A5. If you keep the R generator, then you also have the double coverings, A4 prime, and so on. And there's a lot of literature, and I will not have by any means time to go over this. So you can check the slides. There is over 100 papers at this moment now on this topic, since the paper of Perugia. But okay, the groups are isomorphic to the known usual groups. Now, as I promised, the fields transform in some way, so we should be able to write superpotential with them. You should specify the representation under this rho, and you should also specify the weight kappa that was entering this new scale factor. Now, it may be that you can write the superpotential term with a set of fields, but generically, you also have tau transforming. So the most general situation is where your superpotential will contain the fields transforming like this, and also functions of tau. And they have to transform in nice ways so that you can form a singlet, which is what you keep in the end. So these functions of tau, they organize into multiplets, so they transform very similarly to the field. They have a weight, they have a rotation, and they are the modular forms. Okay? To build singlets, you should have, I mean, in all these tensors here of the rows, you should have a singlet, but also you should cancel the weights. Now, this is nothing so special at this point. So you may wonder now, why is this so nice? And what I can tell you is that since this is SUSY and we are requiring homomorphicity, this is a function of just tau. And it turns out mathematicians know these functions quite well. Functions of a complex parameter in the upper half plane, which transform like this. They are not so many. In fact, they form finite dimensional spaces, vector space. Let me give you some table. If you are working with A4, there is just one triplet when K is 2. So this is the only thing you can put in the Lagrangian. At 4, there are 2 multiplets and so on. So we are very constrained, and you cannot put everything you want in the Lagrangian. There is some structure. Okay, so this is very abstract up to this point. Let me give you an example. We can work together how to build, let's say, a Majorana mass term for right-handed neutrinos. Okay, so let's try to put 2 right-handed neutrinos together in the superpotential and give a Majorana mass term. Let's work with the modular A4, which is isomorphic to gamma 3. And let's put them in a triplet of A4. So far, so good. And give them weight 1. So the exponent in the scale factor is 1. Now, what can we put in the superpotential? Well, n with n, the weight becomes 2. But if we want an invariant superpotential, we have to cancel that part. So we need some function of tau with weight 2 to cancel the weight of the field. And there is only one choice. Okay? You can only put, I mean, if you go back 1 slide, you see that for A4 there is only this choice at weight 2. So this is what you can write. Coupling, then you only have 1 singlet. Actually, you only have 1 because this is 3 times 3, gives you 1 plus 1 prime plus 1 prime prime, plus a 3 antisymmetric, which is 0, plus a 3 symmetric, and that's the only one that you care about. So explicitly, if you go and do your Clebsch coordinates, you find this matrix. And you see that these are not independent parameters. I mean, you have a scale, fine, and then you have tau. If you fix tau, this is all known, because all these functions are well known. Okay? So now we can, to build the model, I mean, I'm not going to do everything, I'll just show you, because as I told you, the literature is too vast. Now that you know how to make a modular invariant term, I can show you a modular invariant model, which is based on S4 and it's 4 leptons, which was done in collaboration also with Asymptote. So we chose the group. We have to choose the field contents, and once you do that, you will get a superpotential, which is this one. So there are parameters: alpha, beta, gamma, G, G prime, which is the only one which has a physical phase, and lambda. And of course there is tau. So everything is fixed in terms of these guys. So you can minimize your chi-square fit to data and see what if you can get a fit. And you cannot always get fits. So it's not that that it's so easy to get the data. But in this case, you can. We found a fit. Especially, we found a fit even if you get rid of that phase. Okay. So I'll jump over this detail, but we found a fit with 7 input parameters to 8 observables which are well measured. I mean, they are 12, but 8 are the ones which are well measured. And we have some predictions. Okay, and some correlations are implied within the parameters, but we can fix things within their 3 sigma ranges. Okay, so now you are experts on modular symmetry and model building. So now I can talk to you about the new parts of what we did in this written paper. Okay, so what's new? And what's new has to do with hierarchies of fermions, which is something which would be very nice to have. But usually in these models, we are putting them by hand, which is very unsatisfactory. It's very uncool. So we either have hierarchies. This was not shown in the previous slides, but this was happening. There, in the fit, we had to put in by hand hierarchical parameters, or maybe there is some cancellation happening. So how can we do something about this? There is one approach in the literature, which is actually, there are two papers which are not don't have such a great overlap, but they both share one author, and which is Steve King. And this approach, these approaches basically rely on the following: you add scalars, and they turn out to do something like a Frogat-Nielsen. So what plays the role of the Frogat-Nielsen charges is not the Frogat-Nielsen symmetry, but you have the weights playing this role. Okay, these kappas. Here, what I will show you is not going to be so similar. So first of all, I don't want new scalars. I don't want new scalars. I want just to use the modulus tau. It would be great. Then in our approach, also there is this difference that we don't have something like this, like Frogat-Nielsen charges. In fact, for the three generations, we have the same weight. So how does our approach work? And those of you who were here in the morning maybe will follow this more easily. So Ivo talked about stabilizers. Let me review a bit. First of all, when you scan these modular models, I mean, you build your superpotential, you want to compare with data. You can restrict yourself without loss of generality. If the theory is fully modular invariant, you can just look at this region here, which is called the fundamental domain. Okay? And as I told you, as soon as you fix tau, you break the modular symmetry. Now, there are special points, special values of tau, as you've also said, told us, the stabilizers, for which you get something, you still get something in the end. Let me say that again. Generically, you break the modular group, but at these special points, when tau is I infinity, or tau is equal to I, or tau is equal to omega, which is this cube root of 1, okay, this point here. When tau is equal to one of these three, then what happens is that you don't break the full modular group, you just have something residual, some generator that you don't destroy. And if you are here, you are preserving a Zn. If you are at tau equal I, you are preserving a Z2. And if you sit at tau equal omega, you are preserving a Z3. Now, the key idea is that when you are at one of these points, you are constrained by one of these symmetries. So what naturally happens at one of these points is that some couplings vanish. So if you sit at a symmetric point, like tau equal I infinity, you can have zeros in your mass matrices. And this is appealing as an approximate thing, but we don't like it as an exact thing. So we want to generate from these hierarchies. And it turns out that if you go a bit away from the symmetric points, all these zero entries will be populated by powers of epsilon, where epsilon is the distance to the symmetric point. Okay. Now, of course, the next step is to find out which powers of epsilon, but you get already the idea. No, we have something like that in the symmetric point. We go a bit away from that, and we start to have powers of epsilon. And hopefully, you get enough powers of epsilon to get the hierarchy of fermion mass. So, how to determine these L exponents, these dots? First of all, what values can they even take? So, if you have, if you sit close to tau equal I, you can have entries of order 1 or order epsilon. That's it. In fact, this case was explored in a paper which came out just as we were finishing ours. They focused, so it was Ferruccio, Valerio, Andrea, and Arseni. They focused on the group A4. But as you can imagine, if you can only have entries which are 1 or epsilon, you cannot get the three, naturally, the hierarchical masses. In fact, they got the electron mass, which was 0. We don't like that, so in fact, we will restrict ourselves to these two cases. So being close to omega, where you can have entries which are 1 epsilon or epsilon squared, or even close to I infinity, which close to infinity means large imaginary part for tau. And then your entries can go up to epsilon to the n. Okay, how do we determine these powers? It's the decomposition, as the title says, the decomposition of the fields entering the bilinear under the residual symmetry groups will tell you in the end what are the powers of epsilon. And I'm writing this here, so these are abelian groups. Even if you have a triplet, it will break down into 3 singlets. And in general, these guys depend on weights and so on. And we found all of them for all representations that we had for the usual modular groups. We listed in Appendix A of our paper, where we can find them easily. You can find them easily. I know you won't even go to Appendix A of our paper. Anyway, so let me give you an example again, so to understand what is going on. And we can take a bilinear and choose, for simplicity, a triplet of A5. Let's work with A5 and another triplet of A5. Now, what you find with triplets of A5 is that when tau is close to infinity, so has a large imaginary part, they decompose like this. A5, so the symmetry at infinity is Z5. You have 5 1D representations, and the decompositions of the triplets are these. What this tells you with our analysis is that you will have corrections to the entries of the mass matrix, and you get something like this. Okay, so the entries of the mass matrix are basically proportional to powers of epsilon. The powers are dictated by what these guys are, and epsilon is something which vanishes when you get to infinity. And this is what we expect. And in fact, if you go and put these 2 guys in a superpotential and with the appropriate modular forms, you will find the Fermion spectrum, which is 1 epsilon to the 4. So it's hierarchical. So this seems like a nice result already, intermediary result. And before going on, I'd just like to point out that this looks a lot like Froggatt-Nielsen, but this is not Froggatt-Nielsen. So Froggatt-Nielsen, you have order 1 coefficients for each of these entries. It's not the case here. They're all related between themselves and with superpotential parameters, and they can be less than the number of entries. So in a sense, this can be said to be more powerful than Froggatt-Nielsen, if you like. We can discuss this also later. All right, so this is the example. Now, of course, we try to do some systematic scan of all possible Fermion spectra you can get with all possible small groups, with all possible representations and weights. In fact, we did this. This is one example of a table we have in another appendix, which you probably won't check. And I just show that some patterns are not hierarchical and others are. This one is the one we just found in the previous slide. We did also for the other group, so this is A5, but the other tables are bigger. Some of these are also hierarchical and interesting, but they will have 3 copies of the same singlet, so in the end they will not be so predictive. You have too many parameters in the superpotential, and we want to be really predictive. So we will collect, and I collect in this table the most promising ones with the less number of parameters for each group, for each vicinity of each symmetric point. And the patterns you will get is 1 epsilon squared, 1 epsilon to the cube, and our good old friend 1 epsilon to the 4. And I'm hiding purposefully this part of the table because it's horrible, so it will make you run away. All I want to keep from this set of possible representations are the biggest ones, which imply less parameters in the superpotential. So let me just jump as fast as I can from this to this. So we tried leptons, the lepton sector, and the representations that you see here, which are, let's say, the biggest dimensional, they should have the least number of parameters. And we fit them with success with 8 parameters each. So we're done, and thank you. No, I'm joking. I would be done here, but there was a problem. Yes, I know. 2 minutes is enough to tell you that my fits, our fits are fine-tuned. So while you can fit the data, we're still not happy. Okay, so we can fit the data, but we are not explaining hierarchy. We're not taking full advantage of this because there is some fine-tuning. And why are we getting fine-tuning? Well, you can imagine why. If you go to a symmetric point, you're not just constraining the entries of the mass matrix, you are indirectly constraining also the mixing. So if you get the wrong PMNS in the symmetric point, there's no use in going in using that model because you will need fine-tuning to get the correct phenomenology. So we checked what are the conditions to get PMNS close to what we observed. At most, you can have a 0 in the 1-3 entry when you are in the symmetric point, but no more zeros anywhere else. And turns out the conditions to get this, the restrictions on the representations, were already found by Agi and Andrea Romanino. There are two conditions essentially on what the representations need to decompose as. I mean, don't look at it too much. It's a lot of notation. We added two rather trivial conditions that they didn't have. Okay, and what we had is to apply this filter to that previous table to find really the promising models. And we did just that. Here is the table, and I will cover with a donut with most of it because I don't care about this mess. What I want to tell is, unfortunately, we lost the 3 times 3 prime of A5, which was very promising, right? The 1 epsilon epsilon to the 4. It's a shame. You cannot get the correct mixing in the symmetric limit for leptons. What we did find next in list number of parameters is a 3 for EC and the 3 singlets for L. Okay, so this would be a possibly a viable model for S4 close to tau equal omega. And so this we explored. We scanned 0. So result of the scan, we found one very good model. I mean, one very good model within the context. This is the representation. You may look more to the matrices. So there is first line is proportional to 1 epsilon to the 0, epsilon epsilon square. So in fact, you will get the hierarchies of charged leptons. This is the Fitts values. They are not particularly fine-tuned. Last slide on the model is the next one, where I tell you that the mixing is not fine-tuned. So indeed, you are explaining naturally the masses. You just need to be in a vicinity of, this is omega. This is a zoom on the fundamental domain, and this is the cube root of 1. So you need to be at a distance 0.02 of it, but then everything follows, and you even get some predictions. Not too many predictions, but still, it's interesting to find that such a model exists. So I have 0 seconds. Let me just give you my summary. First part is I hope to have convinced you that there's something here. So modular symmetry is an avenue maybe an avenue for flavor model building, and Fermion mass hierarchies can maybe naturally arise in this setup as I try to explain. Okay, thank you very much.
Thank you, João, for the very clear talk about some very interesting topic. We have time for questions. I see one in the back again by Claudio. Gentleman in the pink shirt, which is not Antonio.
Thanks for the nice talk. One question concerning, I mean, in string theory, people working in string phenomenology, I mean, they've been working on free fermionic models and so on. I mean, free fermionic models, special compactification, special points of symmetries, P2 cross P2, and so on, or Z3 cross Z3. I mean, and they use also, you know, techniques of modular invariance because, and they've done predictions in the past, I think, of, you know, neutrino mass matrix. Have you made contact with that, or are you aware of that? Or, because this seems to be looking at what string theory does from the, you know, bottom up, let's say, right? Yes, so there should be a contact with people that tried already 20 years ago to sort of compactify, you know, Calabi-Yau, whatever, some special points where the computation were simpler.
Yes, so I can tell that the approach is different, and it's not yet clear exactly how they glue, but indeed we expect right at the top down gives us something which throws away some models from the bottom up, which are nonsense from string point of view. Let me just flash, if I can change the slide, maybe you have to click. Okay, let me just flash some references. So there was some work by Niles et al. I don't know if I included it here on eclectic flavor groups. So they tried to get something which came from a more reasonable top down, and they have shown that you don't get just a modular symmetry, you maybe get additional flavor symmetries when you do that. So this is what I know. I'm not an expert at all on the top down part, but it's a very interesting question. Thank you.
I think if I recall, they also not just get some symmetries, but restrictions on the representations.
Yes, I believe so. There is a table, right, in one of the...
I think so, but we should check the reference. Alexei has a question? No, no, the other one first. Sorry.
I want just to clarify this issue of fine-tuning.
Yeah.
So as far as I understand, you have in your superpotential different terms which actually produce mass to the same particles.
Yes.
And in fact, in superpotential, we have additional parameters, which probably are this alpha, beta, right? So it's not just you cover, you have on the top some additional parameters. And then fine-tuning is when you try to, for instance, contributions to different masses.
Yes, exactly.
Well, this is...
So what I can tell you...
This is unfair.
No, okay, what I can tell you is that we had to take some care with this, right? Because as you say, we have tau, which fixes epsilon, and we have the superpotential parameters. I mean, you see them here. Now, fine-tuning is a delicate issue because you can measure it in different ways. One way we can look at it a posteriori is if these errors are large or not. Okay, they're not, but this doesn't say there is no fine-tuning. Next thing we looked at was try to use in the paper some Barbieri-Giudice measure of what happens if you vary these parameters. Do you destroy, for instance, the ratio between the square mass differences of neutrinos, which is 1/30 around that? And we found that it was not particularly large, the Barbieri-Giudice. But I mean, there are various ways of looking at fine-tuning, and what I can tell you is that we try to give something which at least is an improvement over the previous results of modular fits. I don't know if this answers your question.
All right, Antonio, it's your turn. You already has the microphone.
Very nice. Yeah, very nice talk. Just curiosity, because this has supersymmetry, and besides these nice explanations for the flavor problem that you want to seek for, which predictions do you have? What is the implications of having supersymmetry? The phenomenological implications.
So actually, in this case,
the scales.
Yeah, in this case, to try to avoid breaking these nice predictions, but you have to take care with several effects. Let me jump to backup because, yeah, so apart from RGs, you have to arrange that the SUSY breaking terms are not ruining your predictions. And in fact, Ruiz and Criado have shown that there is some regimes where, as long as you arrange a hierarchy between the scale of SUSY and the scale of SUSY breaking mediation, you can get regions of parameter space where these constraints from modular symmetry are not completely spoiled. But this is still a framework which needs some work and some consolidation. I mean, you have problems with the Kähler, which have to be taken into account and so on. So there is a lot to do here yet still. And just a second comment that I almost forgot. So you are talking about observables. This is, as I may have not stressed enough, but this is very good to constrain things which are in the superpotential because they're allomorphic. It's allomorphic. In the curve, it's not so because you can take the modular form and the conjugate, and then you have infinite terms. So for SUSY breaking, I mean, we tried even once. People remember we tried to get something, but it's there is no strong constraint from modular symmetry alone. In let's say mu3 gamma, unless you add some field.
We have a final question over here.
This is a very general question. Actually, in a way, you are trying to hide some supersymmetry or cope with some predictions which are not straightforward, some results which are not straightforward. But as a matter of predictions, if you want to test a model, you need to make predictions.
Yes.
And predictions doesn't mean postdictions.
Exactly.
Which I've not seen any prediction here. Unfortunately, these mentalists have worked too hard. I wish they would have kept secret the theta 1,3, for example, which we predicted. But okay, I wish they would have kept it secret so that we could still test the theorists. And the only thing which is not fully measured for the moment, I think, is the phase or the very precise value of some angles.
Yes.
So is there any one brave enough to go into predicting something which has not been measured already?
This is a very honest comment, yes, because in fact, it would be very nice if they would kept the exact numbers so on, apart from some groups. Now, look, as you say, this is post-diction. So what we're trying to find is a model which at least reproduces with some ease what we see. And then it would be nice to have predictions. There is some work with applying this to find effects in neutrino oscillations like non-standard interactions. Also, Perullo and Ding, they have a paper on that. But I agree with you. At this point, it's just that trying to get the minimal number of parameters to predict, to post-predict something. Yes. There is.
It's for the Zoom as well.
The counting of parameters is a bit tricky because, okay, you can put symmetries and have very few parameters once you have chosen among 25,000 models. And you still have only 3 parameters, forgetting that there is another space we have been playing with.
That's true, but it also applies to the standard model without a flavor symmetry, right? You can also just fit the numbers. They're just 9 3x3 matrices in the standard model, and you fit to the experimental.
Well, you don't even need to fit the matrices because not all the elements of the matrices are physical. You have redundancies in the parameterization. No, I mean, okay, the standard model doesn't make any claim. It's approximately the most stupid model one can write. People have always complained about its lack of symmetry. They didn't want chiral quarks, they wanted vector light quarks all the time. Well, it was a fight for 10 to 15 years because that seemed to be too inelegant, too asymmetric, and so on. It's true, but here, okay, if there is something compelling, it's nice. If one has to work so hard, then at least there should be a prediction.
Yes, no, this is the idea, to try to find models where you work less and less and find something more natural like this hierarchies. So I agree, a lot of structure is not good. It's a waste of time.
All right, thank you everyone, and thanks again to Jean-Pierre. And now we will continue to another Portuguese speaker. And now we have another João Gonçalves. It's a very common name in Portugal.
Is the LP levels the third one? That one.
All right, it's we have then João Gonçalves is going to tell us about deep learning searches for vector-like leptons at the LHC and electron muon colliders. Please, João.
Okay. Hello. So hello everyone. Today I'm going to talk about some of the work I've been doing over the past few months with some external collaborators. And this particular work is going to be based on our most recent paper that came out on arXiv last month. We have the reference here. And it's particularly going to be talking about deep learning searches of vector-like leptons, TLHC, and electron muon colliders. So what's so interesting about studying these new particles? Okay, so vector-like leptons from a theory point of view are very well motivated. They usually arise from low energy limits of either gut models or string models. And there's a lot of phenomenology to study from this new physics. In particular, one generation of vector-like leptons is enough to induce mixing patterns in the charged lepton sector, which may lead to lepton flavor violation. And also because they couple directly with the standard model charged particles, they will also induce corrections to the anomalous magnetic moment of leptons. However, despite this well-motivated background, there has been very limited searches at colliders. In particular, there's been only one direct search at CMS, where they do a search for vector-like leptons that couple dominantly to the tau lepton, which for the purpose of our work, as I will explain later on, is not as relevant. And there's also some searches at lab that put these vector-like leptons at around 100 GeV. So the framework that we're going to be using to do our phenomenological work was originally inspired by a gut model based on E8, but instead of doing the full low energy limits, we're going to simply use very simplified frameworks. It's pretty much standard model plus vector-like lepton plus the right-hand neutrino, and we also consider both scenarios whether the vector-like lepton can either be a doublet or singlet of SU2. And the right-hand neutrino, based on this gut model, is going to be around the keV mass range. We also consider a global failure symmetry, which makes so that the vector-like lepton couples only to the muons, and we parameterize this mixing via angle alpha. And the neutrino mixing is fixed just in such a way that the PMNS is valid. So one characteristic of the model that is very interesting is related to its decay width. So one of the dominant decay channels for the vector-like lepton is the two-body process, with the vector-like lepton decaying to the neutrino and the double boson that follows that Feynman rule. And what we did find, especially in order to be consistent with some with the G-2, as I'll show later on, is that the cosine of alpha that appear in that mixing matching needs to be order 1, while the singlet of alpha is relatively small. And this Feynman rule, the nominate decay, for the doublet case, we'll go with the cosine of alpha that you mix, which means that since it's order 1, it's going to lead to a relatively big decay width. Whereas for the singlet case that you mix, you go with sine of alpha, which is small, so the singlet case will narrow it as opposed to the double case. And here I have a plot just to show you the overall behavior of the decay width as a function of the mass PRL for different values of that you mix, so you can see the type of behavior you expect to see. So one of the things we're going to be studying here, we need to look at constraints coming from G-2, because the BRLs will directly couple to the muons, either via a Higgs boson or a Z boson. The contributions I show here. So for the Z boson, actually the contribution is going to be relatively small. That's because, as you can see, the G-2 scales with the squared mass of the muon. So the Higgs contribution is going to be the dominant one, as you can see, because it scales with the mass of the VLL itself, which is going to be taken from 200 GeV to 1 TeV. Because we also have mixings with the VLLs in the sharp lepton sector, we're also going to induce some flavor violating decays, particularly involving the muon. And for that, all the points that we use for numerical analysis must pass these constraints, and we use Fino and Flavio to do this type of computations. So let's start with some results. So this is the first plot I want to show. So this is the G-2, the contribution from both the Z and the Higgs boson as a function of the mass of the VLL for 1 sigma and 2 sigma bounds. And the blue lines and the black lines correspond to different coupling points, which I show in at the bottom. But the main message here is that for the entire mass range, I am able to find sets of points that are able to be consistent with G-2. And this is for the doublet model. For the singlet model, I can find the exact same thing. So sets of points that are consistent with this observable. One thing that I mentioned earlier is that the Higgs contribution, the Z contribution is really small and can be completely neglected. As such, I can assume that the Higgs contribution is the only one that is important. And I can use G-2 as a way to constrain the coupling of the Higgs to the vector-like lepton. And that's what I show here using G-2. So I plot the product between the right and left chiral Higgs couplings as against the mass of the VLL. And you can see here is that for around 100 GeV, I can get couplings, product couplings around 0.02. And up to 1 TeV, I can go as far as 0.010. So they're relatively constrained. And just to complement these results further, we want to see, okay, what happens if I just put the couplings up to the perturbative limit? What kind of mass range I expect to see? I can explain this anomaly. And what I find is that up to like 1200 TeV, up to which is the limit of the perturbative in the coupling, I can expand G-2. And again, this is valid for both the doublet and singlet models. Okay. So basically all okay, so the G-2 analysis basically to do some benchmark points to be used then to do the full collider analysis at the LHC. So we're going to be hunting for the single topology, which is single production with a W boson. We apply a very simple selection criteria to do background single separation. And the main idea here is to use neural networks, in particular going to be utilizing a genetic algorithm that optimizes the construction of the neural networks and maximizes the statistical significance. So the algorithm, the genetic algorithm works in this way. So I have the diagram for you to easily follow. But the idea is when I do construction of neural networks, I have various parameters and functions that I can use and fine tune. And there is no ultimate formula to select which are the best ones. So to do this algorithm works to try to find those sets of hyperparameters. So the idea is I start with a list of different hyperparameters where I construct random models. I train those models. And then at the end, after the train, I pick the top 5 best ones. And from those top 5, I select mother and father pairs. And from those mother and father pairs, I extract hyperparameters and construct new ones, which I dub the daughters. And then from the daughters, I add some probability of mutation, train the daughters, and do this cycle over and over for a given number of generations. And at the end, I have the best models that maximizes my metric. In this case, I want to maximize the significance. So this is the LHC analysis. For the lepton analysis, it's going to be a much more simpler analysis because, as you are aware, the vector-like leptons are singlets of color. So while at the LHC, production of color particles are heavily favored, what you expect is that Electron Colliders electroweak processes are more favored. So you want to do a quick analysis on here, focusing on pair production topologies on the S channel. And this again is going to be focused mainly on the singlet model. So let's start showing some results, starting with the LHC. So this gives you an idea of the type of cross sections we have for both the singlet and the doublet model. As I showed to the left, the cross section function of the mass. And that's right, I focus on a particular point at 700 GeV. So what you see for the doublet model, I have relatively decent cross sections, 0.49 femtobarn. As you can see, for the singlet, I have really low cross sections, like 10 to the minus 6. In fact, if you do some naive calculations on the expected number of events at the luminosity phase of the LHC, for the doublet model, you get around 1,000 events. At one singlet, you get you don't get pretty much nothing. So all the points that I will show later on, where I do computational statistical significance, I always make sure that is above a limit where I get at least one event. So to train neural models, I won't need data, and the input that is just going to be kinematic distributions of final states, and includes like pseudo rapidity, missing energy distribution, and the transverse momentum of final states. So typical distributions that you find in this type of analysis. So this is for the double case at 700 GeV, and for the single case, you have very similar type of distributions. So all the main results are summarized here. So in this last column, I show the G-2 at each mass point, and then I show the statistical significance for 300 femtobarn for one free type luminosities at 3,000 inverse femtobarn. And I do the computation of that significance for 3 distinct statistical metrics. So I have the most common one, the S over square root of background, and then I'll also consider these two, the Z minus 1% at ZA. So this is the Asymptote estimate. The difference between the two is how I compute the errors. So for the Z minus 1%, I'm assuming that I know the backgrounds to an error of 10 to the minus 3. While for ZA, I'm much more conservative and I consider systematics of 1%. So then those first two, the S over square root of background and Z minus 1% is the more lenient ones, while the ZA is the more stringent one. So to summarize everything here, so for the double case, I can probe VLLs up to 1 TeV, and this is both for the run free and the luminosity phase. Whereas for the single case, I can only exclude VLLs at 100 GeV if I consider run-free type luminosities. Up to a luminosity phase, I can extend the exclusion to around 200 GeV. This is if I consider all the metrics, but if I only take into account the more conservative one, for the singlets I can say nothing, but for the doublets, I can exclude up to 500 GeV, both for the run-free and our luminosity phase. So this is with the Lhc results, and now for the Electron Colliders, as I mentioned earlier, is a much more simplified analysis where you compute the expected cross-section for per production in the S channel. And as you can see, we obtain very decent cross-sections, order 1 femtobarn, across a wide range of masses, which is superior to what we saw here in the Lhc analysis. We also, for completeness, we also consider per production via photo fusion, which is those last 2 lines in the table, because unlike in the S channel, the cross section typically decreases as we increase the center of mass, whereas the photo fusion processes have this logarithmic dependence with the center of energy, and can therefore play an important role in high energy colliders as well in the low mass regime. And as you can see, we obtain, at least in the low mass regime for these type of processes, we obtain relatively decent cross sections. So this is what I had to show, just to summarize everything that I talked about here today. So we have analyzed 2 very simple extensions, just with a better standard model plus better like lepton, either a singlet or a doublet. We saw that both models can accommodate G-2 within 1 to 2 sigma bounds for a class range of masses. We did some collider analysis at the LHC using deep learning techniques, where we were able to exclude up to 1 TeV if they're doublet, and up to 200 GeV if they are singlets. And for the Electron Colliders, we did a very simplified analysis, and we find we obtain decent cross sections for pre-production topologies, which will allow to prove much wider ranges of masses. And this is what I had to show. Thank you very much for your attention.
Thank you, João, for the nice talk. It's nice to see this kind of machinery being applied from the theory side and not just on the experimental side. We have time for questions, particularly as João nicely finished before his allotted time. Okay. So I'll ask a naive and technical question. What kind of processing units are you using? Are you using GPUs?
Yes, GPUs. Yes. Machine learning is mostly optimized to run on GPUs.
Did you have problems with the COVID-induced shortages of, to get the material?
Well, actually, we ordered some GPUs, but they still haven't arrived. So I had to run all of this on my own laptop.
I see. All right. So it's not just the annoying thing of wearing the masks. All right. Any other questions? I don't see also any from the Zoom side. So
there are some questions in the chat. Sorry for interrupting. There are in the chat.
From the chat, please.
Felipe Joaquim in the chat.
Oh, all right. All right. We have, yes, indeed, for this talk. So Philip Joaquin is asking, I'm repeating so in case people aren't reading, at which order is G-2 computed?
So when you do the computations, so we use these loop diagrams to you consider these diagrams to do the computation of G-2. So with the X was on and Z at 1 loop.
So the answer is at 1 loop. And I think there was another question about the NN architecture. No, yes. And so you can see the question. Why do the NN architectures change with the mass?
Well, when you are increasing the mass, there might be changes on the in the kinematics of the final states. So if there are changes, even if say small changes on the data, then you might need certain different hyperparameters to take that into account.
All right, thank you very much, Philip, for your questions, and I guess we thank again the speaker. We have our next speaker approaching. I'll need some help here.
Yes, please. Oh, yes. Great.
All right, so we're almost ready. This is kind of slightly slower than a pit stop at Formula One. So it's we have now with us Michal Ryszkowski. Thank you.
Yes.
And he's going to tell us about Earth as a baseline for measuring CP violating phase in neutrino oscillations in matter. Please, Michal.
Okay. First of all, I would like to thank the organizers for giving me this opportunity to come here and present my work. And I'll just finish with basic information about neutrino oscillations. So neutrino oscillations are described by PMNS lepton mixing matrix and Hamiltonian in vacuum. So here we have our mixing matrix Hamiltonian. Those are well-known formulas. And yes, those and PMNS matrix and Hamiltonian are characterized by 6 different parameters. 2 of those are neutrino mass differences, which are well constrained, and we have also 3 mixing angles, which are also fairly well constrained. We have also, but we have 6th parameter, this delta CP violating phase, which is weakly constrained, and this parameter will be one I will aim at, will be main focus of my talk. So what changes when we go to the matter? Basically, we have to add to our vacuum Hamiltonian interaction terms. So neutrinos, while traveling through matter, they interact with it, and assuming constant matter density and following work by Ioannidis and Pokorski, they showed that it's possible to write this Hamiltonian in such a way that it has the same form as Hamiltonian in matter. But yes, the same form Hamiltonian matter. So PMNS matrix and Hamiltonian they both have the same form. However, they are written not in terms of vacuum parameters but effective parameters. So we have, instead of vacuum parameters, effective parameters. 4 of them we have changed, but there's one crucial thing, that 2 of those parameters remain unchanged in this parameterization. And this way we are able to obtain formulas for neutrino oscillations in matter in the same form as the ones in matter, but in terms of these effective parameters, which form we know. Okay. So now a few remarks about CP symmetry violation. There are 2 sources of CP violation in standard model. They arise from weak interactions. So we have one CP violating phase in CKM, the quark mixing matrix, and which is also constrained. And the other one, as I said before, one in PMNS lepton mixing matrix, we have phase delta, which is, as I said before, weakly constrained. What's the significant CP violation? Basically, it can help us explain matter-antimatter asymmetry, and it may be a test of standard model and physics beyond standard model, because knowing the exact magnitude of CP violation in standard model can tell us whether we should look for this additional CP violation sources outside of standard model or not, and maybe it can point us to the models which contain CP violating terms or not. So basically, the question is, what is the value of delta, which will give us the magnitude of CP violation, leptonic CP violation, and neutrino oscillations may provide us with an answer. So as for CP violation in neutrino oscillations. So for neutrino oscillations in vacuum, performing CP operation means that we just exchange in probabilities, we exchange neutrinos for corresponding antineutrinos. This is equivalent to exchanging this delta parameter to minus delta. Hence, if we have non-zero value of delta, then these probabilities won't be equal, and that is the sign of CP violation. In matters are a bit more complicated. We have those matter-induced effects. However, the performing CP operation means basically, again, changing neutrinos to antineutrinos. However, it's not equivalent to only changing the sign of our delta parameter, but we also have to change the sign of our potential. But as I said before, since this delta parameter is the same one in matter as in vacuum, therefore measurement of this delta parameter in neutrino oscillations in matter will provide us with the information about CP violation. Symmetry violation there. So our approach to measure this delta in neutrino oscillations is based on first of all on the fact that matter can enhance or weaken delta effects on probabilities, and second of all is the fact that probabilities in matter and in vacuum are proportional to 1 over energy, so they're falling rather quickly. Therefore, it seemed the promising approach seemed to be to measure delta seemed to be to analyze oscillations of sub-GeV atmospheric neutrinos traversing the Earth. And what's following is based on this paper published last year. So that's our setup. So basing on PREM model, which says that we can approximate Earth we can separate Earth to 5 different layers, each one with constant matter density, approximated constant matter density. And so we have our neutrinos produced in the atmosphere. They're traversing through arbitrary number of Earth layers. They are hitting our detector under the angle theta. Our detector is deep underground. It can be either Dune or T2HK. We used here Dune characteristics for our calculations. Looking closer at our layers, we have, as I said, in each of the layers we have constant matter density. Therefore we have well-defined form of Hamiltonian and PMNS matrix. Our neutrinos are traveling through the distance x through each of the layers, and this distance can be obtained from like fairly straightforward trigonometric, and it depends on this azimuthal angle theta. So now let's go to see some expressions. Exact S matrix for neutrinos traversing n Earth layers. There's also one thing, we assume normal mass ordering here, but also inverted mass ordering works as well. And this S matrix is just the product of S matrices of S matrices for each of the layers. We can write this S matrix in this form here. So we have some product of rotation matrices and also this epsilon diagonal matrix. And then, so we have exact S matrix. Then from this we can have exact probabilities. However, it turns out that there's a problem that sub-GeV oscillations are much faster than detector resolutions in energies and azimuthal angle. Therefore, it might be a good idea to average probabilities to get useful info out of it. What I mean by that will be visible here. So there's oscillation probabilities as a function of energy for chosen azimuthal angle. We see that these exact oscillations, so that blue line, these oscillations change very quickly. So these are very quick oscillations, which are far above the detector resolution. And this orange line is the average probabilities which we aim for, which may give us really useful information. But the question is how to do it, how to average these probabilities. One may go after numerical averaging, so it has been done already before. However, it is CPU time consuming, and no analytical form of probabilities means that it's difficult to understand behavior of probabilities, and it's difficult to find optimal experimental setup. Therefore, one may go for a different approach to analytical averaging these probabilities based on this PREM model. And I will show how we have done it and what results we got. So first of all, let's take our full S matrix in this form I showed before, and let's notice that between the layers we have always the same this product between 1-3 matrices. And it turns out that for realistic matter densities, they can be approximated by identity matrix. Therefore, we obtain with much simpler form of our S matrix, which the most important part is the product of this 1-2 matrices and this epsilon, which I showed before. Then we can separate this product and S matrix into two matrices. One of them, the X matrix, is just a straightforward 2 by 2 matrix, and the other one has only one entry. That's just one here. Then we can write also our S matrix in the same form, and from now on I will use this. I will use the notation of A and B matrices to describe this S matrix. So we have our S matrix as shown here in terms of 2 matrices A and B. Then we can obtain probability just square the S matrix. It's not yet averaged, but it turns out that the rapid oscillations, the term responsible for this rapid oscillations is this one in the middle. So basically, to average oscillations, average our probability is we just need to average out this term in the middle, and then we are left with average probability in terms of our 2 matrices A and B. Okay. So we also show that it works very well. So comparing to numerical averaging too. So as I said before, B matrix is constant. A matrix is the one we are interested in. So let's go after this A matrix. As I said, it's just the product of U matrices, which are just which are constant, and we have 2 by 2 X matrix. And looking closer, it turns out that X is 2 by 2 symmetric unitary matrix with determinant equal 1. Therefore, it can be parameterized in terms of 2 parameters, alpha and phi. These parameters will give us the later analytical formulas for probabilities. And we either can obtain them from numerical fits or from analytical parameter approximation to them. So we'll have analytical formulas for those, for arbitrary number of Earth layers. So now we'll go after those analytical approximations. So we just have to, first of all, expand this product in our S matrix in terms of small parameter epsilon, which is proportional to 1 over energy. Then we just have to keep terms linear in epsilon, and we obtain very compact and remarkably compact formulas for those 2 parameters in terms of our small parameter epsilon and other nu, which is proportional to which depends only on theta. So those are parametrical. Those are our analytical parameterizations of these 2 parameters. We know how they look like. We know how they work. We know what their behavior. And it's important also to stress that similar approach works for antineutrinos. So we can look immediately at the features of those 2 parameters. First of all, we can know that the phi on the right doesn't depend on energy almost. It slightly depends for lower energies, but going higher it doesn't. Moreover, sine alpha is some function of f of theta divided by energy, so it's 1 over energy. Then one may ask, what's the quality of our approximation? So here we compare numerical and analytical formulas, and it turns out that already for 300 MeV it works quite well, and already for 500 MeV it works really well. So it's almost identical. So the conclusion can be that this parameterization works already for more than 300 MeV. So now we can apply that to the result number 1, which is analytical formulas for average oscillation probabilities. So we have our average oscillation probabilities in terms of 2 parameters, which we know they form, and we know how they behave. And then we can just obtain probabilities in terms of those. And here's one example. Here we have delta dependence, and apart from that, we know how all of those terms work. So basically, we arrived at analytical understanding of average probabilities, and this may give us better chance for delta detection. In matter of fact, we're not interested directly in probabilities, because there's roughly twice as much of muon neutrinos produced than electron neutrinos. Therefore, the more useful quantity that gives us roughly number of neutrinos observed by detectors is this one. So we have to sum the probabilities, and this is the formula for this quantity. Again, it's very similar, straightforward. We know all of this. We know all of the ingredients of it. Result number 2, basing on this, we were able to obtain optimal azimuthal angles, so angles optimized for delta detection. Basically, on this plot, we have they are denoted by vertical lines. We can read them out of the plot, or just find the extremas of this function, or basically extremas of this sine to alpha. And these angles are written right here. And finally, result number 3 for us was we are able to propose observable that is optimized for delta detection, for delta measurement. Basically, that's the observable that has strongest delta dependence. So looking at this formula, we see that this part doesn't have delta dependence, the other one has. So we have this sine delta plus phi. Therefore, it was maybe not that straightforward to propose this observable, which is some sum of this PE quantity with some energies. So after doing some calculations, we are able to arrive at this formula. So we see that we have just some term which depends on sine alpha, which just multiplied sine delta plus phi. So we have here we have some term that is proportional to our sine delta plus phi. So there is our delta dependence. So we can look how it behaves. How does this optimal observable behaves? So we see the resemblance of a sine-like behavior. So that also follows from this formula. Moreover, we also moreover, we also can see how these optimal azimuthal angles behave. So these three are optimal angles. They have much bigger amplitude than random angle chosen here. Okay, this is done for energies 400 MeV and 1000 MeV put into those formulas. So to sum everything up, main results of our work were the general formula for average oscillation probabilities in terms of two parameters, which we obtained analytical parametrization. This allowed us to get analytical understanding of average probabilities, and moreover, this analytical understanding of this quantity which give us the more realistic number of detected neutrinos. Following, we are able to obtain optimal azimuthal angles that were aimed at maximizing delta detection, and finally, we're able to propose optimal observable that also was aimed at maximizing the chances of delta detection. What's next? Just last 2 points. One may perform much more realistic analysis, including experiment, characteristic, and simulation. That's what can be done. The next, maybe we'll do it in the future, and basing on Duno T2HK experiment, and maybe apply similar approach to this PREM Earth model to other celestial bodies like stars, neutron stars, or something. Okay, thank you very much. Yeah, that's it.
Thank you, Michal. I already see a question there.
Well, it is known that the CPU evolution pattern in neutrino sector depends on whether neutrino is Dirac or Maran particle. Could you please comment on this in relation to your studies?
In our studies, it did, like we show, no, it didn't matter. The Marana phases, as far as I remember, didn't matter for this study. That's yeah, that's what I can comment for. Yeah, it might be. Now our work was only aimed at this at delta without looking at the nature of neutrino masses.
We have another question over there. Yes, please.
Hi. Maybe this is a basic question, but is it possible to distinguish between normal and inverted ordering using matter effects and oscillations?
I mean, as far as our study goes, it would also work for reverse ordering, so we'd also be able to derive all those formulas. But that's more general question, and now I don't feel like I simply don't know if that knowledge. Yeah. Maybe I don't know. Maybe we would be able to obtain different formulas, different results for inverted ordering or normal ordering, and then we be able to compare it to experimental data and then get some information from this. But it would require some careful handling of that.
Like Lingo and Orca experiments precisely are using matter effect and propagation inside the Earth. And the probabilities are different, especially in the GeV range.
Thank you, Alexei. I don't see questions from the Zoom side. Let's check the chat just in case. Shall we? Maybe not.
Let me check the chat.
Okay, let's proceed with the final speaker of this session. And thank you. Yes, thank you. For that.
Does it work? Yes, it works, right? Perfect. So the slides are in the computer. I've sent it to you. Yeah, I'm just using it. Also, I have like a pointer. Okay.
All right, so let's get the slides on.
S1 plus 5 presentation, the second one.
All right, so
This is the second slide.
show it again. And you can go back with your pointer. Yes, exactly.
Okay,
so we have now Socrates Trifinopoulos. He will tell us about minimal explanation of flavor anomalies, B meson decays, muon magnetic moment, comma, and G-2, I already said, and CAA is the Cabibbo angle anomaly, I believe. Go ahead, please.
So, hi everyone. Thanks for having me here. It's a pleasure to be in Corfu, which is a crossroad of my native Greece and the country where I'm doing my postdoc now in Italy. So here you can see a view from Sissa of the Trieste Bay. Today I'll be talking about the recent work I've done with David Marzocca, with this big title that you heard already. So let's start with this set of flavor anomalies with B physics anomalies. So as you've already heard from the talks today morning, in recent years, anomalous results from various experiments that specialize in B meson physics have been reported and attracted a lot of attention from the community. So the two different categories, the neutral current and the charged current transitions. So we start with the neutral current, and in particular this B2S LL channel, where there's a deficit with respect to the sun and mole prediction. It's primarily encoded by this ratio, RK and RK star, which is almost free from hadronic uncertainties because they cancel out. So the theoretical error is less than 1%. So it is rather clean observable. And as you can see here, it has been measured by Barbar and Bell with rather large errors in the past. But also there's a 3.1 sigma deviation reported from LHCb quite recently. And then we also have our K star here. Okay, the sun model is 1. And we have in the lower bin of Q square, where Q square is the environment mass of the electrons, a 2.1 deviation, sigma deviation, and 2.5 in the rest. So we may add some more observables that are relevant to this channel, and they only add to the current trend and offer a rather coherent picture. So, for example, B2S mu, where here the smallness of this boundary ratio is also theoretically quite, it's controlled quite precisely with a few % of error. And moreover, we can add branching ratios of B2 hadrons containing a strange quark and muons, and also P5 prime, which is an observable that has to do with the angular distributions in B2K star mu, and it is historically the first one where we saw an anomaly. So our case survived the recent analysis by LHCb, and it even strengthened the previous trend. So if we vary the new physics Wilson coefficients one at a time, various groups have found that the overall deviation amounts to even more than 5 sigma. So what I find more important is that there's been analysis quite recently, which is using a rather more conservative method and allows for new physics effects in all of the Wilson coefficients. Plus, it uses the most general structure to the loops that are relevant to the non-perturbative effects, and still finds 4 sigma deviation. So that is why I named this the good anomaly. So if confirmed, it will be a new physics signal, because lepton flavor universality, which is one of the features of the Shannon model, will be violated. Yeah, you'll know it's an axial symmetry in the limit of vanishing lepton Yukawas. And due to the fact that the gauge couplings are larger in the Shannon model, decay rates, which differ only by leptons, are predicted to be the same in the Shannon model. So it's also going to be of short distant origin because it can be shown that at operator level, long distance effects can only induce universal shifts and no LFU violating effects. Then we have the Truscan anomaly. Here we have a 3 sigma deviation in this ratio, B to D tau nu over B to D and light leptons. And I'm naming this the maybe not so good anomaly because, as you can see, the concern is that it is mainly driven by Babar in 2012. If we exclude it, we find 2.2 sigma. And as you can see, Bell, recent measurements have found that D agreeing with the Sana model. But yeah, LHCb has not measured at D yet, so maybe we are in anticipation of an analysis. Then we have the anomalous magnetic moment of the muon, which has made the headlines this spring. And here we had a long-standing result from Brookhaven, which was recently updated, as you know, by Fermilab, and confirmed the previous results, even increased the significance to 4.2 sigma. So why is this guy maybe the bad guy? Because it has ignited some fighting between theories, because there are 2 different methods to calculate the Sana model prediction. And this 4.2 sigma depends on the R ratio calculation, which basically uses analyticity of the amplitude and connects the hadronic polarization vacuum diagrams to data from electron-electron collisions. But recent lattice results are quite closer to the experimental results, so it's still unclear what will happen there. And finally, we have the Cabrillo angular anomaly, and I named this one the ugly one because first it involves nuclear physics, which are plagued by a lot of uncertainties, and then it concerns a lot of different ways to determine the same parameter. It's this VUS, and they are independent with each other. So the situation is quite complicated. So first, we have a disagreement between VUS extracted from the tau decays, which have a rather large error, and the ones from the kaon decays. And then we have an even larger disagreement with VUS as extracted from super allowed beta decays. Basically, there you extract VUD, and then you perform, you connect it to VUS by CKM unitarity. And there, the result is highly dependent on theoretical calculations, and depending on the input, there are 3 groups working right now. At the moment, you can get from 3.6 sigma to 5 sigma deviation. So maybe I tell you a little bit more about what's going on there, because it's the most recent anomaly, and maybe you've not heard about it. So super allowed beta decays are the most precise ways to determine PUD, up to 10 to the -4 precision. And what are they? They're Fermi transitions between isobaric analog states, where there's also no parity violation. And so they're mediated at 3 level by the vector part of the charge currents. And they are protected against renormalization effects by strong interactions due to the vector conservation hypothesis. But beyond 3 level, you have electroweak radiative effects that involve the axial current, and they dominate the error in the extraction of VUD. So we have this master formula here. So this FT here is characterizing all the beta decays, depends on the transition energy, branching ratio of the transition, and the half-life of the parent state. And we write it in this form here, where we factorize all the nucleus-dependent parts in this corrected half-life. And here we have the universal contribution due to the electroweak corrections. So it is universal and independent of the nucleus involved in the beta decay because it comes from the high energy regime of mainly this diagram here, the W gamma box. One more thing to notice is that we will need this later on. Here it was used, the G Fermi as extracted from muon decay. And so what is new here in this box? Previously, it was calculated by using perturbative QCD at high energies and an interpolating function at intermediate distances. But now there's a new analysis, which is a hybrid analysis. It uses both dispersion relations and connects to neutrino antineutrino data, and also lattice QCD results in the regions where they complement each other. And so this accounts for the shift. These three groups are working on it, and they all find a deviation. So, of course, a full lattice calculation would be highly desirable in this case. So, now going to the inspiration of the model, and we return to the B-physics anomalies. And I have to say that in order to devise an ultraviolet complete explanation, this has been proven as a very difficult, notoriously difficult task. One of the main issues is that you have a three-level process in the charge current. You have to compete against three-level, whereas in the neutral current you have a loop-level process. So there the effect can be much smaller. It points towards a very, very weak interaction, 10⁻⁵ of G Fermi actually. And because you also have additionally CKM and GIM suppression. And so there's been only a handful of models out there in the bibliography so far. So in the case of B2SLL channel, it has been shown by model-dependent analysis that you can singly modify the Wieser coefficients of these two operators, these semi-leptonic for Fermion operators, in a correlated manner. So C9 minus C10, for example, equal minus C10, new physics can resolve the anomaly. And you notice that also into B2C tau nu, the same type of operators, these semi-leptonic operators, can also provide a solution there. So it has been become clear to the community that the only viable solution so far that can generate this kind of operations and also be consistent with all of the other low energy data are leptoquark solutions. Additionally, if you include right-hand couplings, which can generate a top-enhanced loop due to this left-right breaking, two leptoquarks, two scalar leptoquarks can also provide a solution to G-2, the S1 and R2 leptoquarks. And then going back to the Cabibbo anomaly, these authors here have pointed out that it can be alleviated if one introduces a constructive interference in nu2e nu. And how is this done? So remember, I told you that we're using G Fermi from this channel here in the master formula for VUD. So if one enhances the G Fermi there and VUD is reduced, then you can account for this success in the US that we are observing right now. So the sensitivity to new physics is mainly due to this enhancement factor here, which is order 20. So this delta is the amplitude of new physics over the standard model. And finally, there is a mild tension into this test of lepton flavoring resulting in tau decays, which it has been known already that from the EFT analysis of the anomalies, of the B-physics anomalies, leptoquarks could play a role there. And since we are touching again these purely leptonic amplitudes in connection with the CAA, we might see these observables also as a link between these two set of anomalies. So let's go to the model. It's we are extending the particle content of the standard model with just two new particles. S1 is the leptoquark, which is a triplet plus U3, and is hypercharged 1/3. And then we have the singlet of scalar singlet, hypercharged 1. And this is the Lagrangian, which uses Yukawa type terms. Here we have lepton doublets connecting to phi, and here we have the quark doublet and the lepton doublet connected to S1. And finally, we also include right-handed couplings between UR and leptons, right-handed leptons. And okay, we have that gauge symmetry enforces anti-symmetry of the lambda couplings, so we do not have these terms on the diagonal. And due to phenomenological constraints on mu3 gamma, we also choose this to be a small parameter. Then we do not need to couple the first generation, and we also don't need these two couplings here, so we do not consider them in the fit. And these are the couplings that we have then. And see how we solve the anomalies. So we have a 3-level mediation of S1 that can cure the RD and RD star. And notice that we do not have purely left-handed contributions. They are subleading. And then here in the B2SLL, we can have a box diagram in which both S1 and phi participate. And this is the largest contribution here, the second term. The other two terms are coming from boxes with only S1. Then we have for CEA 3-level with the phi here, which modify the mu decay, and also at 1-loop level we're closing the loop with the top, and we have a contribution with S1 penguin. And then finally, this is the diagram that generates a contribution to G-2, again with the S1 leptoquark and right-handed contribution. So we have performed a global fit of all the relevant observables, and the analysis prefers rather large masses for these mediators. This can be understood by the fact that the B2SLL scales as lambda to the 4th over m squared, whereas most of the constraints are lambda squared over m squared. And here you can see into the planes of the relevant parameters that solve the anomaly, that we can accommodate all of them at 1 sigma level. So this is the best fit point. And so, for example, for the B2SLL and for the B to C tau nu, the most relevant constraints come from BB bar mixing and B2K nu nu and tau to mu gamma. Whereas for the G-2, we have tau to 3 mu, tau to mu gamma, and this LFU ratio in tau decays being the most relevant constraints. And here we map to the preferred regions in terms of the observables of interest. And again, okay, the colors are not so great with PDF, but here basically are the 68%, 95% confidence level for the B2SLL anomaly, and here it's for the Truscan anomaly. We are again in 1 sigma region, and here we solve the CAA, and as a byproduct of the framework, we can also explain this tension in the LFU violating tau decays. So we go to future prospects. And as you have seen, we are very close to the BB mixing at BTK nu nu bounds, so we expect to see some effects there quite soon. We have the unique signature in B2S mu E channel, which will be probed half of the parameter space by LHCb, whereas in B2K nu nu, all of the parameter space of the model will be probed by Bell. And due to our particular set of couplings, we do not have effects in B2S tau as opposed to the most famous other solutions that exist so far. Here we also have the other LFU ratios where we expect effects, and Bell will be able to probe them. But we also have lepton flavor number violating tau decays, tau to mu gamma, tau to 3 mu, and tau to mu EE, with an S1 penguin, as well as tau 2 E gamma, tau 2 3 EE, and tau 2 E mu mu with a singlet. And these are also we expect them to be improved by LHCb and Bell by 1 order of magnitude at least, and we are going to start seeing effects here in our model. So direct detection is out of question. The masses are too large. Maybe we can have some effects in high energy tails of the Young, but the ideal machines would be future circular collider for the laptop park. And this 5 here would make fireworks in a mu collider, which is one very interesting new proposals. And we also have the model independent prospects. So we will know about the V-physics anomalies hopefully by when Bell reaches this luminosity here. G-2, the runs 2 and 3 have already been completed. So there, the error, the experimental error will shrink even further. But as already mentioned, we have some still work to be done in the theory, different methods on the theory prediction. And about CEA, we can advance our understanding of the electroweak radiative corrections even further with some lattice calculations maybe. And existing precise measurements of VUS will be improved. So K to pi L nu, LHCb, Na62 and TREC, and K nu over K3 nu by J Park. But there are also even more complementary observables that can become competitive in the future. For example, pion beta decays and the neutral lifetime. So we expect also a lot of progress there. So coming to my conclusions. So there are good reasons to consider all 4 major deviations from the sun model in flavor physics. In our case, under the same lepton flavor universality violating framework. Since we cannot really probe this, or possibly we will not be able to see these mediators in LHC, then in order to pinpoint the nature of the flavor structure, one is forced to consider a set of deviations and not one at a time, as it is done already in the B-physics anomalies, for example. So in this work, we provide the first solution that combines all 4. And the particle content is surprisingly minimal. Actually, it can be shown that it is the most minimal from if one tries to add to the existing solutions. For example, U1, you would need 2 more particles, one for G-2 and one for the CAA. And we have leptonic interactions, which have not been considered so far for the B anomalies, solving B2SLL. And we have a lot of all the new signatures for this model. So thank you very much.
Thank you. We see already one question over here.
I'm sorry, I probably missed it, but what is the mechanism which allows you to account in the same time for the large effect in the B to K, in B to D, and in the small effect in B to S?
Well, we do solve B to C at 3 level and B to S at 1 loop level. One would traditionally expect new physics to arise. So this S1 is one of the very few mediators that can actually do a 3-level solution to
can you show again?
Yes, I'll go back.
The Lagrangian?
Doesn't go back. I don't know why.
So by choice, the couplings of your leptoquark are such that it doesn't come at 3 level in the B2S.
B2SLL cannot be mediated 3 level by S1.
Okay.
So it cannot even couple. Yeah.
No. I remember the model. Thank you.
All right. I see we do not have questions on the Zoom side. I think there's a question by João Penedo here.
I recall, I think David gave this presentation of your model to us before. Wasn't there some issue with the couplings being non-perturbative?
Yes. So
is this fixed? Or?
We have calculated the RG evolution, and this is actually a model which we expect to encounter some new dynamics quite fast, actually. So even 30 dV. So all this is one of the pathologies for this scalar leptoquark models. And yeah, we currently work on some strong dynamic solution for us. But yeah, this is the low energy picture.
All right, I see no further questions, so let's thank the speaker again. And for the last 5 talks, we picked up a total of 10 minutes delay, so maybe come back from coffee at 18:35 instead of 18:30. Cheers. Enjoy the coffee.